Hi, welcome to Lesson 14a, Limits. The goal of today's lesson is to learn what a limit is and how to determine limits of given functions. The concept of a limit is absolutely essential, crucial when discussing differential calculus. We're going to be seeing that limits are going to be absolutely necessary for the development of the idea of determining the gradient of the tangent of a curve at any point along the curve. The first thing to mention is that a limit itself, the value you get for a limit, is nothing more than a y value. Okay, so we'll discuss that in a second. So I'm going to give you a crude drawing here, just to show you how the idea of limits perhaps work. So let's say that I've got some diagram here. One half of the diagram, I could go off like that too. Let's just say, just for argument's sake, that that's y equals x squared. Okay, this would be a very, very bad diagram or graph of y equals x squared. Anyways, let's just say, just for thrills, that is y equals x squared. So let's say then also that this is the point 2, 4. Okay, so we have this x value of 2 and this y value of 4. So now, in order to discuss the idea, the concept of limits, I'm going to start off with another point up here, some general point xy, somewhere along the curve. And I realize that the y value of this point is some distance above the 4. Okay? Now, if I move this point down the curve, along the curve a little bit, it still has the coordinates xy, but this y value is now closer to 4. So that y value has moved down. It's now down here. It's closer to the 4. If I move this point even closer, again, the coordinate stays as xy, because we're just saying it's some general coordinate xy. We see again that the y value is again getting closer to 4. Now we could quantify this and give these actual real values along the way. So, I mean, if I were to just make up a little mock table of values, I could say, so for our xy point, I could say that x might start out at, let's say, 3, and if this function is y equals x squared, then y equals 9. Then if I move this down to 2.5, so we're approaching, this is from the right side of this point, so I'm approaching from the right. This is 2.5, and 2.5 squared would be something like 6.25, I believe. And then we move this even further, closer along. Suppose we go to 2.1, and then this value would of course be 4.41. So notice how the y value of the actual point of target, the target point or the point of interest that we're looking at, the y value is 4. The point we started with way up here, and I'm just giving an example here, if I started at x equals 3, then the y value is 9. As I slide this point down the curve, closer to this point, see the y value has changed. It's getting closer to 4, like I mentioned before. So now it's at 6.25. Then if I slide it even closer, I move it further along the curve, closer to this point, I see that the y value has gotten even closer. Now it's 4.41, whereas it was at the beginning up here is 9. I could then move this even closer. It's still coordinates xy, of course. I move this closer. Let's say I move it to 2.01. Then 2.01, the y value is going to be 4.0401. So we see that the y value is getting even closer to this value of 4. Okay. So now I can do the same thing on the other side. Let's start this point over here at 1. So this is the coordinate, well, obviously 1, 1. Here's the coordinates x, y. I'll make another table of values over here and do this at the same time now. So we've got this point 1, 1. I slide this point up along the curve along here. Notice that the y value started out at 1 here, and now it's gone up, it's increasing. This y value of that point is getting closer to 4. So let's say we slide it up to x equals 1.5, and 1.5 then gives a y value of 2.25. So that's closer to 4 vertically. And then let's slide this point further along the curve to the point perhaps 1.9, which is getting closer to the y value, and we're getting 3.61 for the y value of this point as the point gets further and further, closer and closer along the curve to that target point of 2, 4. And then I can do one more. I can do as many as I want, really, but let's just, so we don't belabor the point, go up to 1.99, and then when I see the y value, so x has slid along even closer to the x value of 2, the y value of that new point is now even closer, so it's 3.9601. So notice the pattern that's developing here. As we move this point from the right towards point 24, and as we move this second point from the left up towards 24, we see that the y values from the right side are getting lower, they're decreasing, and the y values from the left side are increasing. And notice that if I went even further, I could go to 2.001 and 1.999. We'd see that gradually that these points would be getting closer and closer to the value of 4. And I'll just square these just to give more of a demonstration here. And when I go to 2.001 and square that, I get 4.004001. So notice that the closer the x value, or the closer the point gets along the x value towards this point of 2, the y value is getting closer and closer to 4. Here it's zeroing in on 4 from above, it's decreasing from above, and here it's increasing from below. So what we say is, because we're not going to put this point that we're sliding along this curve directly on that point, we're not going to put this right on that point, we're just going to slide it towards that point. But what we see is that if we can agree that the limit of this point is actually approaching 4. So the limit is a y value that the graph approaches as a point moves along the curve. Okay, as the x values get closer and closer to the x value of a certain point, then the y values continue either decreasing or increasing towards a limit that's approaching this value of 4. Okay, so the notation of a limit is something like this. It goes, the limit of some function f of x as x approaches some value of a is L. Okay, so we read this as the limit of f of x as x approaches a equals L. Okay, so we notice, of course, also, like from I demonstrated, that the value of 4 is approached from both sides of that point. Okay, Now I'm going to give you a couple diagrams to look at, and what we're going to see is we're going to see eventually that a function doesn't actually have to be even defined at x equals a in order to have a limit. Okay, so I'll show you what I mean. I'll just whip this stuff off. And so we take a look at this first graph here. So here's some function f of x. As x approaches a from below, or from the left, we see that the curve, the function, approaches this y value of L. As the function, as x approaches a from the right, from above in this case, the value, the limit equals L. Okay, so what we can say then, so I can say the limit of f of x as x approaches a from the left equals L. Okay, so x is approaching from the left and the function is increasing up to the value of L. And then I can also say the limit of f of x as x approaches a from the right. Okay, so as we're coming along here, that equals L, because it's zeroing in, they're both zeroing in on the same y value of L there. Then I can say in general then I can say that the limit of f of x as x approaches a equals L. Okay, so this is the left-sided limit, and this is the right-sided limit, and those limits, because those are those two are equal, then that means that the function in general, the limit in general, is equal. So that's the left-hand limit, this is the right-hand limit, and that means the limit in general is equal to L. And in this case also, where x is equal to a, then we know that f of a is defined, and that equals L. It's the same y value as the limit is. Okay, so that won't always happen, but it'll happen. It's happening in this case. Alright, so let's take a look at another example here. So example 2, again, when we go from the left side, the limit of f of x as x approaches a from the left, we're traveling along the left side here towards the value of a, we see that the y value that it approaches is actually L. We see also that the limit of f of x as x approaches a from the right, so as we come along here from the right, that equals L. It's the same y value that is being approached from both sides. So because the left-hand limit and the right-hand limit both equal L, then that means in general, the general limit as x of f of x as x approaches a equals L. Now you may wonder, well, what happens here? This isn't even defined on that curve. So how can the limit exist? Well, the limit exists because both sides of the function are still approaching that same value. It doesn't matter if that exists or not. The limit is where they're approaching, and they both approach from both sides. The function approaches from both sides that value of L, the y value of L. It just happens that f of a, when we evaluate the function at a, that actually equals some other value, which is y2. Okay, so that would be probably like maybe a piecewise function, or this is a removable discontinuity. Okay, but we'll get into that a little bit later. But as you can see, the limit is equal to L, even though f of a equals y2, some other value. Okay. Graph 3 is pretty much the same as graph 2 in terms of the limit. It's exactly the same, except for in this case, we would say f of a does not exist, or sorry, f of a is undefined, because there's a hole in the graph here. Okay, and I'll show you what a hole in the graph looks like when we get to do our examples in class tomorrow. Okay, so the limit still exists, the limit is still equal to L. Okay, now move along to graph 4, and here we've got a limit of f of x as x approaches a from the left, and we see that as we follow on the curve from the left, we see that we're approaching this this point up here, which is L1. And as we look at the limit of f of x as x approaches a from the right, well, from the right side it doesn't match up with the same y value, the same limit as from the left. It's actually approaching a little bit lower. So it's approaching a different y value. So in this case, because the left-handed and the right-handed limits are not equal to each other, therefore we can say that the limit of f of x as x approaches a in general does not exist. Okay, we can't have a limit if the function is approaching two different y values for the same a value or the same x value. Okay, so this is when the graph or the limit does not exist. And again, here in this case as well, for graph number 4, f of a is not defined because there's no actual point there. Okay, so that would be another hole. Okay, so that's some of the some little examples of limits, and I'm just going to slide this up a little bit and just give you one last little thing to think about. So what I was showing you before with the left hand and right hand limits. So if we can say this as the two-sided limit, or the limit in general. Two-sided limit, or the limit in general, can be written as the limit of f of x as x approaches some value of a equals L. So that's the general limit. And that exists if and only if the left-hand limit, the limit of f of x as x approaches a from the left equals L, and the limit of f of x as x approaches a from the right also equals L. Okay, so these two one-sided limits must be equal to each other in order for the general limit to exist and to equal that same value. Otherwise, if they do not equal, these two one-sided limits, if they do not equal, then the limit in general, shouldn't be a fraction. The limit as x approaches a does not equal, it's just that it does not exist. Okay, so that's the basics of limits. We're going to be looking at limits of graphs and limits of functions tomorrow in class when we go through some examples. But what I'm going to ask you to do, as always, is I'm going to ask you to look at page 346 and look at example 1, and please allow the self-tutor to read to you and kind of explain the solution to you, and then take a quick look at page 346, exercises 1 through 4. And that's what we'll be assigning tomorrow for practice. So we'll take a look at examples tomorrow to hopefully clarify things, and that's about it for limits. So thanks for watching, and we'll see you in class.